All right, well, hello and good morning, and thank you for being here at 8 a.m. And I look forward to seeing you all at 8 a.m. All right, we'll get started. I posted our syllabus, and I don't know if there's anything I need to go over here. Someone's music playing over there. Okay, let's see. We meet here. I don't know. Okay, well, anyway, what do I need to cover here regarding the syllabus? These are our textbooks. You should be able to download them for free as long as you're connected to the UCLA network. So while you're here, you should just download them now, okay? And then if you go home and you need them, then you have to connect via the VPN. And do you guys know how to use the VPN if you live off campus? Okay. Just look up UCLA VPN, look up the instructions and install the software, and then you'll log in. You gotta authenticate with Duo Mobile and stuff like that. But these textbooks should be free. If you click, I think, let's see. Yeah, you should be able to click download all chapters. It'll say up in the top right-hand corner, it'll say brought to you by the UCLA library. Your tuition money funds our library, and our library has access to all kinds of stuff. It's truly a wonderful resource. And then the other book comes from SpringerLink. Again, if you go there while you're on the UCLA network, you should be able to just click download book PDF, okay? And of course, if you feel like spending $80 to get a physical copy, I'm not gonna stop you, but with a PDF, you can do like Control F and it searches, right? So that's pretty nice, okay? But yeah, I mean, if you like having a physical version, that's also nice. Okay, our grade breakdown, lecture view quizzes. I'll explain what that is in a moment. If this is your first class that you've taken with me, for some of you, this is like your fourth class with me, and I would say like you should diversify your instructors, but it's always good to see you guys. Okay, we have homework. The homeworks are tough, but that's also the point, that they're good exercise, okay? Midterm exam, final exam, and we have that, and then there's Campus Wire. I think you should have received an invitation to Campus Wire. I think when I sent it out, it said most of you already had an account, but that's what we have. Okay, grading, straight scale, I don't curve. Okay, so regarding lecture view quizzes, let's see. If you go to Brew and Learn, let me switch to student view. Week 1, Monday, that's today, lecture view quiz. So this is how this is what I do instead of attendance. So rather than counting how many students are here, and I have a suspicion that being an 8 a.m. class, it will be tough for some of you to show up at 8 a.m. And I don't begrudge you. Of course, I love seeing you actually here, and like my vision is like, I mean, I can see, but then like when I'm teaching, I'm only really able to see like the front 2 rows in the center here. So if you want me to like know who you are, my recommendation would be to sit like right here. But of course, anyway, would love for you guys to come to class, but it's tough. It's tough. You got to go to bed like by 11 p.m. the day before, and in college, sometimes that's tough to do. So if you can't come to class, it's being recorded. And as long as you watch the video and keep up with the material, I'm happy with that, okay? And the way I kind of make sure you keep up with the material is via the lecture view quiz, which looks like this. A few questions with just multiple choice answers, no context, and I just say, you know what, the answer to the first question today is the letter C. You'll jot that down, and then you'll fill it out. So you'll just, you have to pay attention minimally when you're watching the video or you're actually attending class. So yes, that is the first answer for today's lecture review quiz. The letter C, I believe, yes, letter C for the first answer, and then I'll give you answers to question 2 and 3 later today. Okay, so that's how we do, instead of attendance, lecture review quizzes. They close the day, they close before the next lecture, so our next lecture will be Wednesday, so they close before Wednesday 8 a.m., so you just have to make sure you respond to it, either Monday or Tuesday, and then the Wednesday one you have until the following Monday, so you have a lot more time for the Wednesday one. But for the Monday lectures, make sure you do it within that kind of 48-hour period, because they close, and that's it. So that's that. Also, make sure you don't misclick. Okay, just take a moment to just make sure that the answers you've clicked are correct, and that's that. And then if you just do that, that should be a very easy 10% of your grade. Okay, and that's lecture review and quizzes. Okay. All right, academic integrity and plagiarism. I always kind of do just a little bit of a spiel. You're going to get the condensed version today. During my first lecture, I like to talk about grades in life, but I kind of have to trim that out today because we have a lot to cover. So the homework assignments, they are tough. That is by design. I mean, some of them might not be that hard, but the point of me assigning the homework is to give you guys some exercise in that it's appropriately challenging, and by working through them, you learn and get a better grasp of the material. And if you've already heard my spiel about this, I always like to compare doing the homework like exercising at the gym. And the point is that when you lift weights at the gym, it's that the process of lifting weights is what's going to make you stronger and better. And you don't go to the gym to lift weights just because we want weights lifted up off the ground, right? If that were the case, you could hire somebody to lift the heavy weights for you, and you would say, okay, great, we did our work today. But the point is that by actually working through and forcing yourself to do the lifting of the weights yourself, that's going to make you stronger. And similarly, regarding the homework, by going through the process of working through the homework, thinking about it, coming up with the solution and writing it out, that's going to make you understand the concepts better. It's going to make you a better, programmer, or give you a better understanding of the topics. Okay, if you resort to copying someone else's solution or looking up solutions or something like that, it's like asking somebody at the gym to lift the weights for you, and that defeats the point. That defeats the point of the exercise. So I want you to work through it. I want you to struggle through it. I want you to accomplish it yourself. And if you can't, if you struggle with it, come to office hours. I'm happy to try to help you. And also, I want you to be okay with just saying, what, I did the best I could, and I couldn't do it. This was what I was able to do. I'm okay with not getting 100% on my homework assignment, right? Don't confuse the goal of, your learning versus just getting a grade for the homework, okay? Your learning is more important than the grade for the homework, in my opinion, okay? So I hope you can judge your performance in the class based on what you learned rather than just how many points did I get on these assignments. Okay. All right. I'll have to save my spiel about grades in life for another lecture. Some of you may have already heard about it or heard it. I give the same spiel almost every course, but I want to get into the material and cover this. What is this class about? And we'll start getting into the topic itself. Okay, so this class is Monte Carlo methods. And I don't know if you have any exposure to Monte Carlo methods prior to this class. In short, Monte Carlo methods use random sampling, repeated random sampling, as a way to estimate a numeric answer to a problem that would be difficult to answer analytically. It's kind of like a brute force method to getting an answer that you couldn't solve mathematically and analytically. So there's a lot of problems out there, a lot of mathematical problems, and if you can figure out an analytic solution, that's great. Okay, but a lot of times the analytic solutions are a little bit hard or not possible or just too hard, and so we can use a Monte Carlo method. All right, Monte Carlo method. If you don't have to use it, don't use it, okay? They are not efficient. You know, there's like a joke that says like Monte Carlo method is like the worst way to solve a problem, but sometimes it's the only way to solve the problem, okay? And so we'll look at some problems. A lot of the problems probably we could solve analytically, but we're gonna start off with some of these ones that we can solve analytically and also solve it using the Monte Carlo approach to just kind of show that the Monte Carlo approach is a legitimate method for approximating our answers, right? So Monte Carlo methods, they're computationally expensive. They use like a lot of computational power, and you only get an approximate answer. So those are kind of like two thumbs down, not super great things about Monte Carlo methods. On the flip side, the analytic approach just might not be possible. And so sometimes we have to resort to Monte Carlo methods, okay? A little bit of history. Monte Carlo methods were developed during the Manhattan Project. This past summer, the Oppenheimer movie came out, and it was all about the Manhattan Project and stuff like that. And I was like looking to see if one of the characters was going to be Stanislaw Ulam. I was like, oh, I know that guy from the Manhattan Project, but I don't think he made an appearance, which is too bad, but that's okay. Basically, there was, they were trying to figure out some of the math. The math was really, really, really hard. And so they decided to try to approximate it, using basically this newfangled thing called the computer. They had the ENIAC mainframe computer, and they kind of coded out, a way to kind of solve this problem, right? Stanislaw Ulam was inspired, I guess, when he was playing card games of solitaire, and he was trying to figure out, like, how many, like, sometimes, you guys ever play solitaire? How many, when you deal out the deck, how many of these things are actually solvable, right? Like some of these solitaire things, like you can't win. They are impossible to win, right? But then it's like the math behind it is really, really tough. So one way to kind of approximate a solution is, all right, well, why don't you just try playing a whole bunch of games of solitaire and see how many you can win? And that might give you an approximate ratio of what percentage are winnable, okay? And anyway, they applied this to, I don't know what math they were working on regarding the development of, nuclear weapons. But, everything was super highly secretive. Everything had to have a code name. And so the code name was Monte Carlo, inspired by, the casino, I guess, like in Monaco, like in James Bond movies, when they do gambling and stuff, it's often at the Monte Carlo casino. So anyway, here's like an example. So Stats 100B, our favorite class, even though I don't teach it, you learn like the properties of probability distributions, right? And we said something like, I've got this random variable x. It's got this PDF f of x, right? How do you find the expected value? How do you find the expected value of random variable x? What do you do? If this is continuous, what's the integral that you solve? Oh no. This is where you're supposed to answer. You're supposed to say, you take the integral of what times what? Dx. Yeah. X times f of x. Thank you, right? So if you want to get the expected value of x, all right, so if x has the PDF f of x, you take the integral of x times f of x dx, right? And this is just kind of your basic definition of how you get the expected value of some kind of probability distribution, right? And this thing, I don't know, fancy x represents the support of x, basically, where your PDF is non-zero. And, if it's the normal distribution, it's negative infinity to positive infinity. If it's the uniform distribution, it's 0 to 1. If it's, whatever else, it might be x for positive greater than 0. If it's discrete, what do you do instead of the integral? You do a summation. You do the sum of x times f of x, and that's that, right? So this is what we learned in 100B. You probably also had like method of moments, and you had a few other things for figuring out the mean of some probability distribution. Okay, and then to figure out the variance, you do something similar, except instead of x times f of x, you do x minus mu quantity squared times f of x, and then so this will give you the variance of your random variable x, and then there's you can rework the math, and you can also calculate it this way: the expected value of x squared minus the expected value of x quantity squared, and this will also give you the variance. And if you have a discrete variable, you replace the integral with a sum. Hopefully this is review or familiar, and we feel okay with this. And then if you have some arbitrary function based off of the random variable, so if you have some function g of x, and you wanted to say, okay, what is the expected value of this function g of x if x is a random variable, then what do? Then you take the integral of g of x times f of x. So you might have some probability distribution for, I don't know, what is your win ratio on some game, and then based on whether you win or not, you can say, what is the probability I'm going to get like 8 wins out of 100 plays or something like that, okay? So you have any arbitrary function, g of x, and you want to calculate the expected value of that thing, you take the integral of g of x times f of x. So these are all kind of integrals that you learn at least how to set up, and for a lot of different probability distributions, you had to kind of work through this integration. And I don't think it's any surprise to say sometimes integration is really hard, and sometimes integrals are intractable or almost impossible, right? You learn some tips and tactics for solving integrals, but a lot of times it's hard. And they have like at MIT, they have the integral bee or something. It's like the spelling bee, but it's like a competition where they have to do like different integrals, and it's tough. And so sometimes we get into a situation where we have some kind of integral and we don't know how to solve it. It's too complicated to solve analytically. So what we do is, rather than trying to get the exact answer analytically, we get an estimate based on some simulated randomness. We just do an estimate. So here's just a very simple example, right? Let's say you have a probability distribution, and you have a way to simulate random draws from this distribution. Rather than trying to figure out what is the expected value of this probability distribution kind of analytically doing the integral of x times f of x dx, we can say, well, why don't we just generate a whole bunch of random values, okay? And if we generate a whole bunch of random values, we can estimate the mean by taking just the sample mean of all of our randomly generated values. So, you know, if you knew nothing about probability rules, and I said, what is the average number that you would get from rolling a 6-sided die? Okay, so like this is simple enough where you could do this, right? So you could do you would do the summation of x times f of x, and you would do 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6, then you would go through it and you would get your answer, okay? But you know, let's say, I don't know, this was before you took your probability class. A simple approach to estimating what is the average number you get from rolling a 6-sided die is just to kind of do it manually. You roll the die, okay, and you write down, oh, I got the number 3. You roll it again, I got the number 6. You roll it again, I got the number 6 again. You roll it again, I got the number 2. And you just do this maybe like 100 times. And then you just add up. You know, you take the average of all 100 dice rolls that you get, and you'll get an approximate answer to what the true answer is. And that's basically what the Monte Carlo approach is. Just approximate it by just doing random sampling. So let's see how much we remember. This isn't an indictment or anything, but chi-squared random variable, 5 degrees of freedom. What is the mean? So what is a chi-squared random variable anyway? It is the distribution of
Square of a normal distribution?
Yeah, you take a normal distribution, right? So you take a standard normal going from negative infinity to positive infinity, most values around 0, and then you square it. That is chi-squared distribution with 1 degree of freedom. What's chi-squared distribution with 5 degrees of freedom? Well, you do it 5 times, and you add them up, okay? And chi-squared random variable with 5 degrees of freedom, its mean is 5, okay? So, oh yeah. Look, we can click Wikipedia, the chi-square distribution. Here we go. If, okay, so it says if z, 1 through zk, so are independent standard normal random variables, then their sum, okay, so we take the square of each random normal random thing, we sum it up, and we get this, and this is going to give us chi-square distribution. So we're going to do this 5 times. And then this is the PDF, and then the mean of something with k degrees of freedom is just going to be k. Okay, so that is our answer. Here's our PDF, and we could go through this. We could use the moment generating function. I'm not going to test you on this. This is, you had to pass 100B to get to this class, right? And so we have some good memories from that class. And the mean is equal to the first moment, which is basically you do the first derivative of the moment generating function. You go through this and you get k. And so we say, oh, chi-square distribution with 5 degrees of freedom has a mean of 5. And maybe you remember that, maybe you don't. Okay. Well, if you didn't remember that, well, we would just go to Wikipedia and we would look up and say, okay, what is the mean of a chi-square distribution? But another tactic that we could use is we could just do the Monte Carlo method. And actually, I won't bother. Here's the code. I would just, I would say, let's generate 10 to the 5, like 100,000 values, okay? And in R, we have this function, r chi-squared, that says generate random chi-squared values. So I'm going to say generate 100,000 random chi-squared values with 5 degrees of freedom. This is going to produce this vector samp, which has 100,000 of these random values. And then I'm going to just say, hey, what is the mean of these 100,000 values? And it gives me 4.993, which is pretty close. It's not exactly the analytic answer of 5, but if all I'm going for is I just need an approximate answer for what is the mean of the chi-square distribution with 5 degrees of freedom, this gives us a pretty decent approximation. Okay, and this is it. This is like the entire class. Is we might say this math. If this math was too hard for us, okay, then we can get an approximate answer by doing this. All right, and that's basically what Monte Carlo methods is. Right. If you can do the math and analytic approach, this is always going to give you the correct answer. And if you can do it, then do it. All right. But sometimes we're in a situation where this analytic math is tough. And so what do? We're going to get an approximate answer doing something like this. And it's very simple. If you wanted to say, okay, what about the variance? Okay. Well, the variance, we have our sample of 100,000 values. And if I just want to estimate the variance, I'm just going to take my 100,000 values that I've already generated, and I'm going to say, hey, what's the variance of these 100,000 values that I've already generated? And it says, okay, your variance here is 9.9789. Okay, the true answer for the variance, if we go to Wikipedia, says the variance is 2 times k. So if we have 5 degrees of freedom, then the true answer for variance is 10, 2 times k. And hey, we got something pretty good, all right? And it was very easy to do this, right? We didn't to do the math behind this. I mean, we could have done the moment generating function again, and that would have taken some time. And in this case, it was quite simple. So sometimes the Monte Carlo solution or approximate answer is quite simple. And sometimes it's just very, very tough. Some of you guys took 102A with me. Yes, right? And then for your homework, okay, and if you didn't, that's okay. But for your homework in one of the homework assignments was this Monopoly thing, where you had to go around the board and estimate the probability of landing on each of those things. That's Monte Carlo, okay? That's a Monte Carlo method where technically I guess we could have written out all of the probability rules and said okay, the probability of rolling these numbers was this, and then if you factor that in, then the probability of landing on this spot is this and all of this. But that would be very kind of painful to work through. Maybe writing the code for the simulation was also painful, but once you write that code out and then you let it run, for 10,000 games or something, you get an approximate distribution of where you might land, and that serves as an estimate of the space probabilities, and that's a Monte Carlo method. Anytime there's simulations involved, that's a Monte Carlo method. Okay, Monte Carlo methods are extremely useful for Bayesian statistics, because in Bayesian statistics we often end up with big messy integrals that are really difficult to work through. Okay, Monte Carlo methods are also very useful when we are in high dimensional settings, because in high dimensional settings the math gets very messy very quickly, and so we do random simulations, and this produces estimates without the need to kind of untangle or work through these hard or possibly even impossible math problems. So this is kind of where we are headed as far as course concepts go. We'll cover some Bayesian statistics. Have you guys had exposure to Bayesian statistics before? A little bit? Okay. Well, if you haven't, I'll cover a little bit here. And then we're going to do Monte Carlo integration using kind of built-in random generators from R, and then we'll also look at how do we generate our own random values if we have some kind of distribution that is not encompassed in R's built-in things. We'll look at other stuff, importance sampling, and then some Monte Carlo methods involve Markov chains, and we'll talk about what all of that is. And so two of our important Monte Carlo methods are Markov chains, and those are the Metropolis algorithm and Gibbs sampler, and that's basically what we'll get through. Okay, so let's talk about some basics of Bayesian statistics. Okay, so in frequentist statistics, we say probability, the definition of probability in frequentist statistics is the long run relative frequency of an event, right? So when we say, I've got a coin and the probability that the coin lands heads is 0.5, the idea is that if you were to flip this coin infinitely many times and keep track of the proportion that it lands heads, in the long run, it's going to land heads, with proportion 0.5. And we use, say, common ideas for frequentist statistics is something like maximum likelihood estimation and confidence intervals. These are frequentist statistics, okay? How does maximum likelihood estimation work? Well, we have some kind of probabilistic model, and we say this is the system that generates our random values, and this system has some kind of parameter. The parameter is unknown to us, but it's fixed, okay? And so we could say, I've got this box, or I've got this bag, and I'm going to pretend that there's marbles in this bag. And we're going to say, some of the marbles in this bag are blue, some of the marbles are not. And I want to estimate what proportion in the bag are blue marbles, okay? And so inside there is if I were to just dump out all the marbles in the bag, I could count how many there are, and I could count exactly how many are blue, and I would know this exact probability theta, okay? But we're going to pretend that this bag is, I can't do that, and I don't know what the contents of this bag are. And so how am I going to estimate that? Well, I can start by just kind of randomly sampling data. So I'm going to say all right, here's my first marble. I'm going to draw 10 marbles with replacement. And if I do this, let's say I get 6 marbles that are blue and the rest are not, okay? And based on this, I would say, what is the maximum likelihood estimate for the proportion of marbles that are blue? So if I drew 10 marbles out of this bag and 6 of them are blue, our maximum likelihood estimate would be what? 0.6, right? Okay, and we could I'll work through the math just real quickly. We did maximum likelihood estimation in 100B as well, or a different class? I don't know. One of these things, right? So maximum likelihood estimate is, argmax theta. We're looking for the theta that maximizes the likelihood. So in our case, we had 10 marbles, 6 of them were blue, okay? The likelihood of this thing for an unknown value theta is going to be, 10 choose 6 theta to the 6, 1 minus theta raised to the 4. And we're going to say, I want to maximize this, find the theta that maximizes this quantity. So what do? I take the derivative with respect to theta. I'm going to set that equal to 0. I'm going to solve, get the critical values of theta, and that's going to tell us what value of theta maximizes this thing, right? So because it's a huge product, it's messy, so we're going to take the log of it, and we're going to say the value that maximizes the log likelihood is also the value that maximizes the likelihood. So we do this. 10 choose 6 is 210. So, log 210, 6 log theta, 4 log 1 minus theta. The derivative of this with respect to theta, the 210 zeroes out. 6 log theta is 6 over theta. 4 log 1 minus theta is 4 over 1 minus theta. Chain rule, -1. Set this equal to 0, and then we solve for theta, and we get theta equal to 0.6. So this is going to be the value of theta that maximizes our likelihood based on the data that we've drawn. So if you drew 10 marbles with replacement, where 6 of them are blue, then the value of theta that would maximize the data, the likelihood of the data that we have, is to say that the theta for this bag, the proportion of blue marbles in the bag, is 60%. That's going to maximize the data that we have. Okay. So that's maximum likelihood estimation, and that's a frequentist approach. And then we could say, okay, now that we've got a maximum likelihood estimate for the proportion of marbles that are blue in the bag, we can now ask, okay, I'm going to draw 3 more marbles out of the bag with replacement, and what is the probability that I get two blue marbles and 1 marble that's not? Okay. So I'm going to say, okay, that's going to be a binomial problem, and we're going to do 3 choose 2, theta to the 2, 1 minus theta to the 1. Is this okay? I'm like assuming a fluency with kind of binomial probabilities and stuff. And based on our maximum likelihood estimate, we're going to plug in 0.6 for theta, and we're going to say 3 choose 2, 0.6 squared, 1 minus 0.6 or 0.4 to the 1, and this is our answer. I'm going to say, okay, if this bag is 60% blue, then the probability that I'm going to get 2 blue marbles out of 3 draws is I go through the binomial probability and I get 0.432. Okay. Does anyone have any objections regarding this maximum likelihood approach to this problem? Yeah? It's an approximation, right? We are assuming that this bag is 60% blue because I drew 10 marbles in the beginning, and out of those 10 marbles, 6 of them were blue. Okay? And so I guess let me cover this slide before I go into this further, right? Okay, with frequentist statistics, we can also create a confidence interval, and I could say, all right, let's create a 95% confidence interval, and I'm going to pretend the margin of error is 9 percentage points. So if we said, okay, my bag is 60% blue, then the confidence interval is going to go from 51% to 69%, right? 0.51 to 0.69, right? 0.6 plus or minus 9 percentage points. And I would say something like, I am 95% confident that the proportion of blue marbles is between 51% and 69%. That would be the interpretation for a confidence interval. You guys learned confidence intervals in what? Stats 10 or your AP stats class? I don't know, is it covered in any of the upper div classes later? Confidence intervals, the concepts behind it? When I teach stats 10, I make a very strong point to say that you're only allowed to say I'm 95% confident, and that you're not allowed to say there's a 95% probability that theta is between 0.51 and 0.69. I don't know if that was emphasized when you guys cover confidence intervals, right? So you're not allowed to say there's a 95% probability. And why are we not allowed to say there's a 95% probability? We're only allowed to say 95% confident? What's the difference there? Yeah. Yeah, so when we talk about probabilities, it's for things that are uncertain. So before I flip the coin, do I have a coin in here? Okay, I don't. But let's say I have a quarter. Before I flip the quarter, I could say, what's the probability it's going to land heads? And you would say there's a 50% probability that it's going to land heads. Okay? And then let's say I flip it and it lands. Okay? Now that the coin has landed, can I ask, what's the probability that it landed heads? Okay? And the answer is, in frequentist statistics, that is a nonsense question. because the coin has landed, there's no longer a probability. It either landed heads or it didn't land heads. You don't know how it landed, so you can only say, I am 50% confident that it landed heads. But in frequentist statistics, it is incorrect to say there's a 50% probability that it landed heads, because either it landed heads or it didn't land heads. And similarly, in frequentist statistics, it is incorrect to say the bag, there's a 95% probability that the bag is, 60% blue, or between 51 and 69% blue, because in frequentist statistics, I could just dump out the bag and count how many marbles there are and count how many blue there are, and that's a fixed value. There's no randomness or probability associated with it, okay? And so in frequentist statistics, the proportion of marbles that are blue in the bag is fixed, doesn't vary, doesn't make sense to talk probability about it. You don't know the exact proportion, so you have to say I'm 95% confident it's between this value and that value, but you can't say there's a 95% probability it's between this value and that value. Okay, that's frequentist statistics. In Bayesian statistics, the proportion that is blue in the bag is not just unknown, okay? We're going to treat it as a random variable. It is not, it's not a fixed value like in frequentist, okay? So in Bayesian statistics, this bag is not something that I can just open up and dump out, okay? We might apply it. So for a bag, it makes a little bit more sense to use frequentist statistics because we can probably just open it up and dump it out, okay? But if you have something bigger, like let's say the population of the United States, and I said, what proportion of the United States is under the age of 18, okay? And if you think about it, I guess there's a couple approaches. One is we could pretend we're in frequentist world, and I have this machine that can freeze time, and if I freeze time, I could track down every single person in the United States, and I could figure out, okay, this person is over 18, this person's under 18, et cetera, and we can get an exact count of how many people there are in the United States and get an exact count of how many people are under the age of 18. Okay? That's kind of like what we would require for frequentist statistics. But the Bayesian approach says, you know what? This is this proportion of people under the age of 18 is subject to random forces, right? Every day people are born, they count as people under age 18. Every day some people die, and that changes the total proportion or total number of people. And so this number, or this proportion that's under age 18, is a random variable theta that's subject to randomness, okay? That there's random things going on. And so it doesn't really make sense to treat it like a bag with fixed proportions that we could just dump out and count, because at any moment in time, the total number of people in the United States is changing. The total number of people who are under age 18 is changing. Every day, some people get older, and some people, have their 18th birthday, and so they are now over age 18, and the number of people under age 18 changes, right? So in Bayesian statistics, we say it doesn't really make sense to treat this unknown parameter as a fixed value. It itself is a random variable, okay? So that's what I have here. So using a random variable does make sense when the unknown parameter is a value subject to random changes, right? So we've got people being born, people dying, and people turning 18, and that's going to kind of change this thing. So instead, we're going to use a random variable for the unknown parameter, and we treat probability as kind of a subjective belief. So rather than saying this is what we have, we could say, all right, we're never allowed to actually look inside this box with marbles or the bag with marbles. And the probability of us drawing a marble that's blue is going to reflect kind of what we believe to be inside this bag, okay? Or similarly, what's the probability we select somebody under the age of 18 reflects kind of what we believe the proportion of the United States, that's under the age of 18 looks like. So, so the biggest difference in Bayesian statistics is that because probabilities are treated as random variables themselves, those parameters have their own probability distributions. And those parameters will then have, basically parameters and stuff, additional parameters that define their probability distributions. So the proportion that is blue in this bag has its own probability distribution. And so now our questions and our calculations that depend on the parameter are now much more complicated because we don't have a single value anymore, okay? We now have a distribution. The value theta could technically be any value between 0 and 1, okay? The proportion that is blue in this bag could technically be anywhere as low as 0, as high as 1. Certain values are more probable than others. So there's a probability distribution associated, and now our calculations are a lot more complicated. So if we think back to this thing, what we originally did was we drew 10 marbles, 6 of them were blue. The frequentist approach said, well, I drew 10 marbles, 6 of them were blue, therefore I'm estimating that this bag is 60% blue. Okay? But to me, that feels a little bit uncomfortable to just say, okay, well, I saw 10 values, and therefore, based on my 10 values, I'm assuming the entire population is now 60% blue. Okay? Because that seems like a very small sample to then make conclusions about the entire population. Okay? And so with the Bayesian approach, we'll say, let's have a probability distribution. And we're going to say, sure, I've drawn 10 marbles so far, and 6 of them were blue. So therefore, I think the bag is around 60% blue, but maybe it's 55% blue. Maybe it's only 50% blue. Maybe it's 65% blue, okay? I want to allow for the possibility that the proportion blue in the bag is not just exactly 60%, but it could also allow for different values, okay? And so I could say the distribution of what this proportion theta could be could reflect something like this, okay? Technically, it could be anywhere from 0 to 1, but we're going to say values around 0.6 are very likely, but also 0.7 is likely, 0.5 is likely, 0.4 is also not 0%, okay? And the bag could be as low as, say, 30% blue, and I just happen to get this kind of weird sample where it was 60% blue. That's also possible. I want to leave that into, is the bag going to be 0% blue? Obviously, it cannot be 0% blue because I did get some blue, right? And at the same time, it cannot be 100% blue because I did get 4 things that were non-blue. But we're going to say, 60% most probable, and values around 60% also fairly probable. So that seems reasonable, but that also makes things more complicated. Okay, wait, before I forget, let me give you your second view quiz answer. Second view quiz answer is the letter C. C as in cat is your second answer. C as in cat. C. So, if I ask this question, all right, so I've got this bag. I don't really know what the proportion blue is, right? the proportion blue is some number. It's some value theta. So far I've seen 10 marbles and 6 of them are blue. So I think 60% is pretty likely, but maybe the value is only 50%, maybe the value is 70%, maybe it's 43%. I don't really know, okay? And then I say, well, if I go to this bag again and I draw 3 more marbles, what is the probability I get 2 marbles that are blue, okay? That question's a lot tougher now, okay? With Frequentist, it was easy. We just said, the answer is 0.6, let's plug in 0.6 and we get this number 0.432. But now, in Bayesian statistics, this value theta is unknown and we have to consider all of the possible values that theta could be. And so, to get into this, we're going to introduce the beta-binomial model here. Okay, so I'm going to take an aside. I'm borrowing an example from this website, Variance Explained. Okay, do we have any baseball fans in here? Okay, a handful of you. All right. So in baseball, you have the batter. And they have what's considered an at-bat. They basically, they get a few chances to hit a ball that's like pitched to them at like 100 miles per hour. It's like really difficult challenge. I don't know if you've ever gone to a batting cage and you get like a 60 mile per hour ball and it feels very scary. And I can only imagine what 100 miles per hour fastball looks like. But anyway, if they manage to hit the ball and then they manage to run and tag first base, that's considered a hit, okay? And one of the basic statistics in baseball is considered is the batting average, and it's the number of hits that they get out of the number of at bats. And again, this is a really difficult thing to actually get a hit. And the highest career batting average of all time, okay, is around 0.366, okay? So a little over, it's less than 40%, a little over 1/3, okay? 0.366. So that's, most of the time when a batter faces the pitcher, most of the time they're out, okay? About over 2 out of 3 chances they're out, okay? In Major League Baseball, if your batting average dips below around 0.2, so this is a batting average. So in baseball, because the batting average is, like, the lowest is around 0.2 and the highest is 0.366, they just kind of look at these numbers and they'll say batting 200 or batting 366 or batting 300 or something like that, okay? So if you're batting below 200, chances are you'll get cut from the team. They'll demote you to AAA or something like that, okay? So it's difficult as a position player to, if your batting average is low, you might get cut. So almost all of the players will have batting averages above 0.2 or above 200, okay? Most batting averages are around below 300. I think the average is around 262.262 is, I think, kind of the batting average for baseball right now. And again, the highest career batting average of all time is 0.366. If a player has a batting average over 0.33 or higher for a single season, that is considered to be very, very, very good, okay? And so the difference between, like, the absolute best of 0.33 and, like, the absolute worst of 0.2, it's a very narrow range, okay? Let's say a team, promotes a player, okay, hires a new player, and we don't really know what this player's batting average is. Okay. And this player in their first 10 at-bats in Major League Baseball, let's say the player gets 5 hits out of 10 at-bats, okay? So far, this player's batting average is 500. They got 5 out of 10. Their batting average is 0.5. Okay? According to frequentist statistics, if we did maximum likelihood estimation, we'd say our estimate of this player's batting average is 0.5. Okay? But anybody who watches baseball would say this can't be sustained through the rest of the season. That this player is not going to be able to keep a batting average of 500 for the rest of the season. I mean, if this player does, this would be like the greatest baseball player of all time, okay? And so our gut and our intuition says that, okay, this player got off to a really good start, but as time goes on, as this player faces more pitchers and has more at-bats, it's going to kind of average out, right? Law of large numbers is going to take over, and it's going to settle down into something lower, okay? So how do we incorporate that into our calculations? If we had to say, all right, what is this player's batting average? If we had to estimate, what is this player's true batting average going to be? How do we do that, right? How do we go from, this is my objective data, 5 hits out of 10 at-bats is 0.5, and how do I balance that with just kind of my wisdom about baseball that says, okay, the greatest career batting average ever in the history of baseball was 0.366, so I highly doubt that this random new player is going to, have a batting average of 0.5, okay? Well, we're going to try to mix in Bayesian statistics, okay? So in Bayesian stats, we will incorporate our knowledge about baseball into what we call the prior distribution. So the prior distribution is, we're going to say, if we don't know anything about a baseball player, what do we think a player's batting average is going to be, okay? And basically, we want a distribution where almost all of the values are above 0.2, most of the values are below 0.3, and pretty much all of the values are going to be below 0.4, okay? So I might draw a distribution that looks something like this, okay? So batting average, as far as a probability, it's a proportion, so obviously the hard limits are 0 and 1, but taking into account our knowledge of baseball, saying the greatest batting average of all time was 0.366, and there's kind of this conventional wisdom that, people don't have batting averages below 0.2, I might draw a distribution like this, okay? That 0.2 is known as the Mendoza line, and it was based off of a baseball player who was very, very, very good defensively, meaning like they were able to kind of like anytime somebody hit the ball, they were able to kind of make the play, like catch the ball, get the person out, and things like that. So they were kept around for their defensive prowess, player Mendoza, but struggled at the plate, struggled to get hits, and so it was kind of you can look it up, but anyway. But this is what a distribution might look like, okay? Where we're going to say, we want to make sure, as far as some batting average for some unknown player, we're going to say it's going to be above 0.2, below 0.35-ish for the most part, and most likely going to peak around, 0.26, 0.27, something around there, okay? Does that kind of make sense as far as this graphic representing what this unknown batting average is going to be? Do we feel okay about this? We're looking for some kind of proportion. And so this, we can mathematically, we can use the beta distribution, okay? So the beta distribution is basically the distribution that we use for an unknown probability, okay? Probabilities are always going to be a value between 0 and 1, and the beta distribution is always defined between 0 and 1, okay? And if we have some random variable theta, the PDF of the beta distribution is 1 over beta function alpha comma beta, theta to the alpha minus 1, 1 minus theta to the beta minus 1, okay? And the beta function with parameters or with values alpha comma beta is gamma alpha times gamma beta divided by gamma alpha plus beta. This suddenly looks very scary because who uses the beta function, who uses the gamma function, and what is all of this, okay? This thing looks scary. It is just a constant. It is just some weird number, and its only purpose is to make sure that when you integrate this PDF, it integrates to 1. That's the only purpose of this weird thing, okay? And beside the point, the gamma function, it's a little weird, but so we're familiar with the factorial function, right? So like 4 factorial is 4 times 3 times 2 times 1, and 5 factorial is 5 times 4 times 3 times 2 times 1. The gamma function is basically, what if you took the factorial function and you just connected it with a smooth line? So 3 factorial is 6, and 4 factorial is, 4 times 3 times 2 is 24, okay? And 5 factorial is 120, right? And so what if you took those points, 6 and 24 and 120 and then times 6, 720. What if you connected that with a smooth line, okay? That's basically the gamma function. That's basically what the gamma function is. It gets really weird on the negative side because if you do like negative values, then like if you have 1 negative value, it's negative, and if you have 2 negative values, it becomes positive. And so the negative side of the gamma function looks like really weird and crazy, but it's kind of this idea of like, if you took the factorial function and if you just connected it with a smooth line, you get the gamma function. But anyway, it's not even important. It's just, this is just some constant so that this thing over here integrates to 1. Oh, I'm gonna run out of time. Okay, you can think of the beta distribution. You got these 2 parameters, alpha and beta, and they are shape parameters as far as kind of like how many yes values and how many no values have you observed so far, okay? And so the resulting beta distribution will kind of reflect what is the probability of getting a yes depending on how many yes and no values that you have. The peak, the mode of the beta distribution will be around alpha divided by alpha plus beta. So let's say your alpha and your beta are 10 and 10, then that means you've kind of seen like 10 yeses and 10 nos. And so the peak is going to be 10 divided by 20, and you're going to have a peak of around 50%. Let's say you had shape distributions 19 and 1. Okay, so you've seen 20 observations, 19 are yeses, 1 is a no. Then your peak is going to be around 19 divided by 20, around 95%. So that's what you have. The beta distribution has more spread if alpha and beta are low, meaning you've only seen a few observations. And if you've seen a lot of observations, then your beta distribution has less spread, meaning you're more confident about what it is. So here's just a whole bunch of pictures. So if you have beta with alpha and beta equal to 1, this is just the uniform distribution. You've just seen 1 yes, 1 no, and overall, we're going to say it could be the true value could be anywhere between 0 and 1, okay? If you have alpha equal to 2 and beta equal to 2, it's kind of like you've seen 2 yeses and 2 nos. And so the most probable is around 0.5, but there's a lot of possibility that it could be anything between 0 and 1, okay? With alpha equal to 5 and beta equal to 5, we've seen 5 yeses, 5 nos. So we're peaking at around 0.5, but now it's tougher to be convinced that the proportion that is yes is 90% because I've seen 5 yeses and 5 nos. Okay, and if I have 20 alpha 20 and beta equal to 20, my peak is at 0.5 and I have a much more narrow distribution. Okay, and as I increase the sum of alpha and beta, here alpha is 50 and beta is 50. Now I'm more confident, even more confident, that the proportion is something around 0.5. So as my alpha and beta, the sum of those get higher, the peak gets more and more focused at 0.5, and we get a narrower distribution. Here I have alpha equal to 1, beta equal to 99. This means I've seen 1 yes, 99 no's. So if I had to kind of guess what is the proportion that is, of yeses, I'm going to get something peaking really close to, 0 or 1%. So we have this very kind of skewed distribution where, the highest values are on the low end here, okay? With alpha equal to 2 and beta equal to 98, we get a peak around here. Alpha 5, beta 95, we have, the peak is, a little bit, closer to 5%, okay? 10 and 90 peaks around 10%, 20 and 80 peaks around 20%, 30 and 70 peaks around 30%, so on and so forth, okay? So, so these are just kind of changing what alpha and beta are. So again, imagine I've drawn 100 marbles out of this bag. 10 of them are blue, 90 of them aren't blue. And if I said, what do you think is the proportion of blue here? With 10 and 90, 10 blue, 90 non-blue, your best guess is around 10% blue, but we will accommodate for values around 10%, 11, 9%, 8%, 12%. But, saying it's 40% blue, we would say, I don't think that's going to be the case. Okay. And similarly, as the values change, if I say I drew 100 marbles and 40 of them are blue and 60 are non-blue, which is basically what alpha 40 and beta 60 means, I got 40 blue marbles, 60 that are non-blue. We're going to say this thing is around 40% blue, allowing for things, maybe it's as high as 50% blue, maybe it's as low as 30% blue, but it's really unlikely that this bag's going to be 80% blue, really unlikely that the bag's only 10% blue if I'm getting 40 blue marbles and 60 non-blue. So here is just some more examples. Alpha equal to 70, beta equal to 30. If I change what my alpha and beta are, I'm going to kind of keep this ratio of 7 to 3, okay? So if I've got 7 to 3 here, I've got 7 to 3, but now 63 to 27, 56 to 24. You could see this spread gets, it remains centered at 0.7, okay? The peak remains centered at 0.7, but the spread gets wider, okay? As I say, so here, I've got fewer and fewer observations. So here I'm saying I've drawn a total of 10 marbles, 7 are blue and 3 are non-blue. What is the proportion in this bag that's blue? This has a very kind of wide distribution. As I change this to say I've got 70 blue and 30 blue, now I'm a lot more confident that it's 70% blue, and we have a narrower distribution. So these are just examples of the beta distribution, okay? As I increase, right, I'm keeping a ratio of 7 to 3. Now I'm saying I've got 350 in beta 150. So now I'm very confident that it's around 0.7, and I have this very kind of narrow distribution. 700, 300, it just gets even more and more narrow, right? So as I increase the sum of what alpha and beta are in these, defining these, the distribution, it gets something more and more narrow here. Okay, let me give you your last view quiz answer. Last view quiz answer is the letter E. E as in elephant. E. E as in elephant is our last view quiz answer. Okay, I gotta kind of zip through our last few slides here, and maybe you'll just have to do some reading on your own. So this, going back to our baseball example, if I want a beta distribution that kind of encapsulates what we believe batting averages in baseball to be, we could use a beta distribution with shape parameters 81 and 219, okay? This is arbitrarily selected. This puts a peak around 0.27, which might be a little bit high. The true average is probably around 0.26 for the entire, all of MLB right now. But basically, this kind of defines this beta distribution that says, okay, almost all of our values are above 0.2. Almost all of our values are below 0.35 or below, 0.4. And, we have a peak something around 0.27 that if I didn't know anything about the baseball player and I had to guess what is a new baseball player's batting average, I might guess that this batting average is going to be something around 0.27, 0.26, maybe a little higher, maybe a little bit lower. And that's what this distribution reflects. Okay? We're very confident that the baseball player's batting average is not going to be 0.4, 0.5, 0.6, or 0.8, okay? Because that's way too high. And we're also quite confident that the batting average is not going to be as low as 0.1 or something, because that's too low to kind of be a Major League Baseball player. So this reflects what we believe to be a reasonable distribution for batting averages. Okay. Maybe that's it. Okay. Last slide number is a little bit off here. Okay. Well, that's it for now. So we'll wrap it up here, and then we will see you guys on Wednesday. Have a great rest of your day. Looking forward to a great quarter. Hope you guys can keep making it at 8 a.m. I look forward to it. All right, we'll see you guys.